This week's video is on dark matter, a strange, fascinating, and mysterious substance, though in some ways I think it is considered fascinating because we call it dark. Dark matter, dark energy, and dark flow, each topics I'd like to cover in the future, have no special relationship with each other. We call them dark because we can't see them. It is a bit like how every new jet plane or weapon gets called X something or other. That X means it's a prototype, and that gets dropped later on. Dark matter, dark energy, and dark flow have as much relation to each other as a prototype assault rifle, fighter jet, and naval cruiser. What dark matter and energy both have in common is that they are thought to make up a huge chunk of the universe. What they also have in common is that they have both captured the attention of the public, which is mostly good, but also means there is an awful lot of scientifically dubious stuff that has popped up around them. I will talk about some of the weirder things we might be able to use the stuff for near the end. It does have some potential uses, but it's also collected a lot of rubbish over the years as people tapped it for its mystery value. And again, the stuff is quite the mystery, but at the same time it also isn't. We've suspected this stuff existed for almost a century now, back to when we first realized we lived in a galaxy. Back in the days of yore, when particle physics had just established that atoms included protons and electrons and not much else, we thought the universe was probably an object of infinite size and age, the steady state model, on the grounds that if it wasn't infinite in size, then if it was infinite in age, everything should have smashed together into one big ball under the influence of gravity. And of course the universe had to be infinitely old, because if it was not, you would have to wonder about what was around before it was, and where it came from. But we were getting good enough with our telescopes to be able to measure the relative speed of a lot of stars, and it established that they were, by and large, moving in an orbit of what we eventually realized was the galaxy. This is where the problem started with the missing mass. We were getting pretty good at doing orbital calculations at this point, and realized based on the number of stars we could see and their mass, everything should be rotating around the galaxy at a certain speed depending on how far from the center it was. Much like how planets rotate around the sun, only a good deal more complicated, since while the sun is one big enormous mass, surrounded by a handful of smaller planets, who perturb each other's orbits just a little bit, the distribution of the galaxy makes the influence of them on each other a much bigger factor in things. We won't go through the math, but there was an agreement that there was a lot of matter we couldn't see. An awful lot too, way more than planets around the stars would justify. This wasn't too big a deal though, we just assumed it was a lot of gas and rock and such, and the orbital models were hardly precise things at that time. Now we had realized galaxies existed quite some time before that. A generation before the United States came into existence, Immanuel Kant had nicknamed them island universes, and it had been speculated a lot of them were flattened disks, like our own is. But we had no idea how far away they were until about the end of World War I, when comparisons of the brightness of nova in them to ones here was noticed to be a lot dimmer, and dimmer to a degree that would indicate they were millions of light years away. This caused what was called the Great Debate about the size and scale of the universe. They still weren't getting called galaxies at the time, spiral nebulae was the normal term, and I've never been able to find out when that fell out of use and galaxies came in. You will see in a lot of very old sci-fi stories or articles references to visiting the Andromeda Nebula, for instance. Now in 1933, Fritz Zwicky, the fellow who coined the term supernova, was at Caltech studying clusters of nebulae or galaxies when he noticed that they had to have way more mass than we could see to be behaving as they did. He estimated the one he was looking at must have some 400 times more mass than he could see, and he called this matter dark matter, though being Swiss he used his native tongue. Now let me give you a quick example of how you could estimate a galaxy's mass, simplified to avoid all the heavy math you need to do this when you're looking at effective snapshots of billion-year processes. Our neighbor, the Andromeda Galaxy, is actually moving toward us. That's not the norm. Virtually every galaxy is moving away from us, redshifting, as you know, and that's what killed the steady state model in favor of the Big Bang. We know what frequencies of light certain types of stars and phenomena give off, so we can look at distant things and say that's the spectrum they should be emitting, but everything on it is moved a bit over. It's redshifted, meaning it is traveling away from us quite quickly. Blue shifting, where the spectrum of stars moves the other way, indicates the opposite. So if I had millions of years to watch the Andromeda Galaxy approaching us, I could say it was going at such and such a speed when I started looking at it, and is now going faster, being sped up by gravity. If I calculated how much faster, I know how much force the gravity had exerted, and be able to say how massive our galaxy was. Same as I could estimate the gravity and mass of Earth by dropping a rock and seeing how fast it got as it fell. In a nutshell, if you do this for all two galaxies, you'd find out they both massed a lot more than the stars in them would suggest they did. Now that's not a problem. We already know a lot more hydrogen and gas is floating around than the stars contain. Add to that, the year before, Jan Oort, for whom the Oort cloud was named, had tweaked to a similar idea, that the mass of our own galactic plane was much larger than we thought. Problem was, his calculations were erroneous, and Zwicky himself was off by an order of magnitude. For a long while, because our data and modeling just wasn't sufficient to really nail it down probably, the idea kind of hung out in limbo. Everyone agreed there was a lot more matter than what stars contained, but this was somewhat shrug-worthy. Seeing gas clouds of hydrogen is a bit tricky but conceptually straightforward. Everything tends to absorb or reflect light, and any given animal molecule has certain characteristics of which frequencies it does this for. So if I'm looking at a star, I know there's some gas and dust between me and it. And if I look at one twice as far away, I'd expect, on average, there'd be about twice as much of that. Start looking at thousands of them and you can start calculating pretty exactly how much gas and dust is between you and each of them, and get a good idea how much junk is lying around in between, and even its distributions. We've gotten way better at this as the years rolled by, and way better at measuring the mass of galaxies, and it started getting very obvious that there just wasn't enough mass out there, in terms of stars and gas and dust, to equal the gravitational force we saw. The discrepancy was just way too big and way too concrete to ignore anymore. This gives us our first two properties of dark matter, because we know it has to have mass, or at least exert gravity, generally considered the same thing, and we know it has to be transparent to light, because it isn't sucking up visual light, or any of those frequencies like radio we look at. Or at least if it does interact with light, it's got to do it very minimally, either by being compacted into huge dense chunks, or just interacting so little we don't notice, being very weakly interacting. That's how things stood in 1980, when I was born and Vera Rubin submitted her results on the galactic rotation problem, showing rather firmly that most galaxies were carrying about 6 times more mass than we could account for from stars and gas and dust to be spinning at the rates they were. This wasn't a groundbreaking and surprising paper exactly, it had been suspected for a while, but she had compiled such a compellingly hard argument and collection of data that it wasn't so much a nail in a coffin as a stake through the heart of the idea that it might just be a mundane source of mass we were estimating badly. This was hard. She'd used the best modern equipment of the time to measure this stuff and spent years compiling it, and every model agreed that for stars to orbit their galaxies like they were doing, there needed to be a lot more mass than we could otherwise detect, either because it was emitting light or blocking it. Now a lot of options were put forth. We had discovered neutrinos, for instance. They'd been theorized since the 1930s and first detected in 1946, and they had some of those expected properties. Neutrinos do not interact with virtually anything. That's why they can glide untouched through entire planets. The problem with using them for dark matter is twofold. First, neutrinos come about essentially as the byproduct of nuclear reactions. When you get a nuclear decay, or a fusion or fission reaction, some of that excess energy flies off as a neutrino. Several trillion of them pass through you from the sun every second, as a result of the fusion of hydrogen into helium. That's the problem though. Only a small fraction of the mass of a star is converted into neutrinos, and hydrogen is hands down the most abundant material in the universe, meaning most mass hasn't gone and been fused and produced neutrinos yet. So neutrinos can't make up the majority of the mass and energy of the universe because they simply haven't been produced in large enough amounts yet. And since they fly off virtually unimpeded, you can expect those from far and ancient corners of the universe to arrive intact at our detectors. So there's no reason to think they got produced in huge quantities at some point early in the universe and we can't see them now. That's the other problem. Neutrinos have very little mass compared to their total energy. They move within spitting distance of the speed of light, and virtually nothing stops them. So they ought not to be hanging around galaxies. They ought to be fairly evenly distributed throughout the universe. More even than photons, since light does get absorbed by lots of things. That's our third property of dark matter. It can't be moving too quickly, or it wouldn't be clumped up around galaxies. It's not evenly distributed throughout the universe. It clumps around galaxies a lot. That means it can't be moving too fast on average. The escape velocity of galaxies is higher than Earth's or the solar system, but it's nowhere near the speed of light. So we can assume this missing mass isn't moving near the speed of light like neutrinos do, or even at a decently relativistic speed, or it would be spread out a lot more evenly, whereas the models that show it exists by making galaxies spin at the wrong speeds indicate it is spread out in a spherical halo around the galaxy. Since it clearly does not interact with light or normal mass, there are no collisions making particles of dark matter slow down and tend toward a disk around a sphere distribution like many galaxies and solar systems exhibit. Gravity would slow them down as they tried to pass us, and speed them up as they neared, so you get nice orbits for those moving slow enough to stay captured, but they will not generally clump into balls like normal matter does to form planets and stars, because they're not colliding with anything to average out their momentum. So that is 3 properties so far. They interact with gravity because they exert it on things and we can see them clumping around galaxies. They don't interact with light or normal matter, or at least do so even less than neutrinos do. And they do not have much speed. We might as well add a fourth too, that they demonstrably make up the majority of the mass in the universe. So that is the state of play for the last couple generations. We have learned a bit more, but mostly why various alternative explanations don't work. Here are some of the more common ones, and their strengths and flaws. WIMPs, short for Weakly Interacting Massive Particle. This is the current favored candidate for dark matter. You could think of this like a neutrino, though in the way a glacier creeping across the landscape is like a snowball. Which is to say, they are both made of ice and moving, but the one is much faster and smaller. If a neutrino is a weakly interacting low-mass particle, a WIMP is an even less interacting heavy-mass particle. Neutrino mass is about 1/millionth of an electron's mass, and 1/billionth of a proton or neutron's mass. WIMPs are thought to be as massive as a proton to maybe 1,000 times more massive currently. Nor would they have to be a single type of particle. There could be a whole particle zoo of these, which would make sense since they are the majority of matter. After all, there are 6 flavors of quarks and 6 types of leptons, of which the electron is 1 and the neutrino is 2. Well, actually 3. Of the 4 fundamental forces, gravity, electromagnetism, and the weak and strong nuclear force, leptons can interact with all but the strong force, whereas quarks interact with all 4. But the gauge bosons, the particles that transmit those forces, usually are said to only interact with the force type they transmit and gravity, though gravity is always kinda tricky to talk about at the subatomic scale. Very loosely though, we'd say each particle has traits that let it interact with a given type of force, and some particles are just missing those. I sometimes think of it like a module or receiver that lets it pick up that force's signal, as it were, and apparently most of the matter in the universe didn't come with that installed for anything other than gravity. Gravity is a weird force. It is way weaker than the other three, and has defied a lot of our attempts to unite the forces in grand unified theories. It's fairly popular nowadays to say it is not entirely real, or maybe not a force, but I reject that. Not because I disagree with the general reasoning, but simply because gravity is the force of the four physical forces we encountered and studied, so if we stop calling it a force, to me that would be like having a definition of automobile that excluded the old Model T. Keeping it simple though, WIMPs would be particles that just don't have the device installed to listen to those other three forces, or have only a very cheap system that barely hears them. Most other particles have the receivers installed for one, two, or all three of those forces. I find this analogy makes it easier to understand why apparently most of the particles in the universe are lacking this trait. Now again, the WIMP is the lead candidate, so it's got more in its favor than against it, starting with quite a few models predicting something like them ought to exist. The big thing against them is trying to detect the wretched things. We've mostly managed to figure out what they are not. Like neutrinos, WIMPs ought to be flying around and through us all the time. But it's kind of hard to detect something whose only known property is that it does not interact with anything for you to detect. I mean, if you had a box full of stuff, you could shine a flashlight right through it and see nothing, wave your hand through it and feel nothing. And while you could detect it by feeling its mass when you picked up the box, they would just slide right through the box, which couldn't have kept them inside in the first place anyway. The big long-standing competitor to WIMPs was MACHOs, massive compact halo objects. MACHOs and WIMPs are fairly inspired acronyms since they are quite descriptive. Where the WIMP is a tiny particle that doesn't interact with virtually anything, a MACHO is a huge macroscopic object that just doesn't emit much light. This is everyone's favorite first suggestion too. Brown dwarf stars, big gas giants, neutron stars that have cooled down, and black holes. Now, halo is important in there because it means the objects are out in the halo of the galaxy. Remember, we need a distribution of matter that implies the missing mass enfolds the galaxy as a loose sphere. A MACHO definitely absorbs light, it just doesn't particularly emit it. They are very dense compared to dust clouds, so we'd expect they don't block much light. This has generally not been a popular solution with the people studying the problem, but more the solution popular with folks not studying it, since it basically represents folks saying, do we actually need to make up some freakish new material composing the supermajority of the universe? In a nutshell, especially these days as we compiled more data and more accurate data, the answer is yes. Now there is a lot of reasons this doesn't work, many of them highly technical, but let me offer a more intuitively simple one that's a variation of the one I use with the Fermi paradox I call the time elapse argument, or T, because I like acronyms too. If I see a weird looking galaxy a billion light years away, and know that it looked like that a billion years ago, then spot a similar one a similar distance away in a different direction, and another in a third direction, I can say that those are unrelated, if artificial in origin, and furthermore that in a volume with a radius of a billion light years, we'd expect 3 of them. So if I look out to a radius of 2 billion light years, which would have 2 cubed or 8 times the volume, I ought to expect about 8 times as many of them, or about 24 of them. Going out to 3 times the distance, I'd expect 27 times as many, or 81 of them, give or take. Going out to say 5 billion, I'd expect to find about 400 of these things. But if they are artificial in origin, you would think they would be more common as the universe got older and more folks arose to build one. As time elapses, you can argue they should be more common. So the further away you look, and the further back in time you look, the less common they should be. If you are seeing a phenomena which appears evenly distributed throughout the universe in space, and therefore time, it is not too likely to be artificial in origin. This works quite well for a lot of phenomena folks have jumped the gun on and attributed to aliens, which has often included dark matter. But it also includes a lot of MACHOs. Planets take time to form. There are more of them now than there used to be. which is a good caveat to the time-elapse argument, since we can't assume just because something is now more common that it is artificial, just that if it is not more common nowadays, it probably is not artificial. Planets take time to form. Neutron stars take time to form as a star must form, live, and die, then cool a lot to be invisible to us. So we should expect that a long time ago, in a galaxy far, far away, it ought to have not formed so much of a massive, compact object halo. Weirdly, what we instead see at huge distances away and back in time are things like dwarf galaxies composed of mostly dark matter instead. But we certainly are detecting dark matter around ancient galaxies absurdly far away in time and space. So that, along with it not being neutrinos, tells us that dark matter is also old. It is old, it is cold, and it is massive. As best as we can tell, it has stayed constant in quantity this whole time too, so it probably does not have a half-life or get created by interactions between normal matter. There are tons of other weaknesses for it being machos, but I think that one is the easiest to understand without needing a lot more science and technology background on it. The next candidate is the axion. This particle was first theorized to deal with some of the problems in strong nuclear force interactions. It is very like the WIMP, except it isn't heavy. Whereas WIMPs can be thought of as a heavy version of neutrinos, weighing as much or more as a proton, whereas neutrinos weigh in at about a billionth of that, the axion weighs even less than the neutrino, anywhere from about the same mass to a millionth of a neutrino mass. Now, the axion is thought to be a particle with a very tiny mass and no electric charge, but it is also thought to switch into photons in magnetic fields. Axions are nice candidates since they are hard to detect but not nearly as hard as WIMPs, both from their properties and that they ought to be somewhere between a billion to a billion times more common. But while it would make a huge difference to cosmology if it were WIMPs or axions making up dark matter, they are pretty similar objects. Theories for axions do place their creation all the way back to the early time of the universe too. In some ways, I would say the axion beats the WIMP out as a candidate for dark matter in the sense that it will be a lot easier to detect. So focusing on proving it or disproving it either gets us the answer or gets it out of the way. And we have a number of experiments just getting underway or coming online soon that ought to settle the matter. We're going to skip the Kaluza-Klein particle, an option for dark matter under string theory. It has not been ruled out yet, but it is supposed to be easier to detect than most of the others, relatively speaking of course, and we haven't got a whiff of it in the experiments we expect to get a whiff from. I will also skip the Gravitino, a particle predicted under supersymmetry. They were a great candidate, but the blows to supersymmetry in recent years demotes them, I think. Similarly, MOND, modified Newtonian dynamics, loosely the idea that gravity doesn't fall off as the inverse square at very long distances, has fallen strongly out of favor, so we will skip it too. That leaves our last big candidate, tiny primordial black holes. Normal black holes just don't form enough to account for all that mass, but a lot of our notions about the moments right after the Big Bang give us some cause to think a lot of small black holes might have formed then. Now, if Stephen Hawking is right, that black holes evaporate with time, with the smaller ones evaporating much faster via the Hawking radiation we talked about in the video on micro black holes and Hawking radiation, then we can put a minimum mass on those. Small black holes don't live long and are very bright, and so not only would the smallest of them be gone by now, but they ought to have left a ton of radiation around all over the universe making its way here. If he's wrong, then no problem at all. A small black hole with no Hawking radiation is a WIMP for all practical purposes. One would fly right through you without you even noticing. But if they do evaporate, we can say they have to have a mass of at least 100 megatons, or they would not be around anymore. One with a mass less than that would not have lived this long, and would have been quite bright. We can push that up a bit too, because there is dark matter in our own solar system. Some models say now it might be denser than expected, possibly a whole large asteroids worth scattered about. And if that's the case, we can put an upper limit on how much radiation they could be spitting out without us noticing them. I would say realistically, we would see them if they massed less than about 100 billion tons, because at that point, you'd expect them to give off a bit less than a megawatt each of radiation and number about 1 million. If they massed less, they would each be way brighter and more numerous. Chop a black hole into 10 small ones, each of equal mass, and they would each be 100 times brighter than the original, and again 10 times more numerous. I'd have difficulty imagining us missing things brighter than a megawatt, and more numerous than asteroids. 100 billion ton black holes would be about as bright as small asteroids and about as numerous. Not that they would be giving off visible light, it would be gamma, but I'd have a hard time imagining us missing even the 100 billion ton ones in gamma. Smaller than that, and I'd say no way. Bigger than that is an option, but not a lot bigger, or we would detect them messing with planetary orbits and picking up accretion disks. Now what's interesting is that while there is cosmic microwave background radiation, there's also infrared and X-ray background radiation. And recently, NASA's Alexander Kashlinsky and others noticed that there was a lot of matchup in those two, with the most obvious candidate for such a match being a primordial black hole. At the same time, we have just recently gotten our first detections of gravitational waves from the LIGO detector, our first sight of black holes and not just things glowing while they fell into them. And it has been suggested some of those detections were of the merger of primordial black holes. I will link an article in the video description from a couple months ago from Shannon Hall at space.com discussing this more. But while primordial black holes have been a solid if minor contender for dark matter for a long while, their stock seems to be on the rise the last couple years, while quite a few of the others have lost some steam during that same time. So WIMPs remain the strong first place, and I'd say axions after that, but I would promote primordial black holes to third place, and we can pursue both them and axions aggressively in the next decade to either prove them or disprove them. There are tons of other dark matter candidates, from the plausible and credible, if minor candidates, to the downright zany. But those are the big ones, and I also mentioned discussing some of the uses of dark matter, so if I don't get to those now, the video will get too long. The first and most obvious use is just as filler material. If you can find some substance or field that lets you interact with dark matter, then there are lots of uses for something that is basically just mass with no interactions. We've discussed quite a few megastructures on the channel that use most of their mass just for gravity, like shell and disk walls. And we would assume you would use hydrogen and helium for this job, since they are so abundant compared to other elements like carbon and iron. Dark matter would, for instance, be even better. You don't have to worry about undergoing any weird transitions into things like metallic hydrogen or starting up fusion if you stick too much in one place. Dark stars, hypothetical stars composed mostly of dark matter that might have been around when the universe was very young, are thought to have been able to get as big as a solar system. Since some hypothetical forms of dark matter are their own antiparticle, you'd expect the rare collisions of two of them to produce a matter-antimatter reaction generating light. This light is why we call them stars, or dark matter stars, or dark stars. You probably would not want to use dark matter as a dense filler in such a case, though it would depend on how often those collisions were happening, but that would make that an excellent power supply too. Obviously, we have no concept for a material or field that could contain dark matter, but if we did have one, and if dark matter was its own antiparticle, you could imagine sticking it in a big balloon or bladder you could squeeze tighter to make more collisions occur, or expand out to decrease them, giving you essentially a massively plentiful source of energy equal to antimatter but way safer, easier to throttle, and naturally abundant, super abundant even. The Bussard ramjet we discussed way back in the interstellar colonization video probably does not work. It seems to take more energy to sweep up the hydrogen it runs across in space and fuse into helium than it would produce in thrust. But if you could do that with dark matter, and it was its own antiparticle, you have an amazingly mass-efficient fuel supply evenly distributed throughout the galaxy that practically has a sign on it saying "perfect rocket fuel." Ships able to gather that up as they plowed by ought to have no problem going quite close to the speed of light and not needing to worry about running out of fuel. If it is not its own antiparticle, then we can still use it, and not just for filler mass. It could be dumped into black holes as power supplies, for instance. Also, I joked once about what I call the dark telegraph, which would essentially be an ultra-dense line of matter between two places where, like any massive object, it contracted space. Keeping something like that from collapsing on itself is a lot easier with something like dark matter. You could send a beam between relay points, or even two overlapping beams going in opposite directions. And unlike normal matter, you can send a laser message right down that beam without needing to worry it would scatter. It's not actually faster than light, but from a practical standpoint, it would be, since along that path space would be contracted so the message would get there faster than normal. If we cannot find an easy way to manipulate this stuff though, there is again the black hole route. Dark matter would be eaten by a black hole whose event horizon they crossed. Event horizons are quite tiny compared to galaxies, but in the long term, like we contemplated in the black hole farming video, you would expect black holes to eat up a lot of the dark matter, gaining their mass energy and angular momentum, which we discussed using in that video. So there are actually some uses for the stuff inside the realm of plausible science, albeit we have to stretch a bit. As we learn more about the stuff, we may learn other uses for it or a way to manipulate it, and I would say we can be optimistic on that score for now, though we also need to be patient. It is not likely we will crack the mysteries of dark matter for some years, and it is mysterious stuff, though hopefully a bit less so now that we're done for the day. Next week is going to be a look at asteroid mining, and we will look at some of the confusion about this topic and asteroids in general. We will probably be spending a fair amount of time in the near future discussing colonizing the solar system. We will also be coming back to discuss cosmology quite a lot before 2016 is over, but I am going to do a poll again. The winner will be next week's video, and odds are most of the next few will be from the runners-up. I'm thinking about switching this over to the website, isaacarthur.net, to just be an ongoing thing, but it will be a YouTube poll this week. Here are the options. First, a look at cryptocurrency, both in the emerging use of it in things like Bitcoin, and how it and related concepts might impact civilizations down the road. Second, a similar topic, folks have been asking me to discuss the concept of post-scarcity societies for a while, and explain what that actually means, and what some of the implications of that might be. For the third option, I thought about taking a deeper look at the concept of a technological singularity. We kind of brushed past it in the transhumanism video, and a deeper look at this idea and artificial intelligence seems appropriate. For the fourth option, we will take a more detailed look at SETI, the search for extraterrestrial intelligence. I'd meant to give it an overview in the video on Tabby's star, but that got almost entirely cut out to look at the anomaly in more detail. Quick channel update. As mentioned last week, the website, isaacarthur.net, is now up, and all the audio is now available to listen to or download at SoundCloud. Regarding foreign language subtitles, which I mentioned last time I have been considering, a subscriber pointed out YouTube has an option I could enable to let viewers submit those, so I went ahead and did that. And on screen is a link to a quick 2-minute video from YouTube that explains how to do that if you want to, and since each video already has subtitles, it does have an expedited method where the timing is already there and you can just click auto translate if you like, then just fix the blatant translation errors. My only request is that no matter how funny some of those automated botches might be, you resist the urge to leave them unfixed for the humor value. Changing sentence structure or wording to be more appropriate to that tongue, I will leave to people's good taste and judgment. This channel's audience usually exhibits a hefty surplus of both. Okay, on that note, don't forget to hit the like button if you enjoyed the video and share it with others. Questions and comments are welcome, and you can try out some of the other topics on the channel. Thanks for watching, and I'll see you next time.